As we approach the topic of acids and bases, every student always starts off by asking, so are we going to melt something? Are we going to dissolve something, right? Hey, is it true that I can take a body and dissolve it in acid, etc., etc., etc.? And while some of those things may actually occur, no, we are not going to be dissolving organic matter. What we're going to be looking at when we talk about acids and bases is, number one, what are they? Number two, what do they do? And finally, how exactly is it that they work? Because, see, acids and bases, it's kind of like gas laws. We've dealt with this stuff our entire lives. We know about it. We kind of fundamentally get it. But if someone asked you, well, what makes an acid an acid? What makes a base a base? Suddenly we're like, I don't know. I don't know. So in this section, what we're going to do is we're going to start off by defining an acid and a base through several different definitions, and we're going to start to take a look at how exactly they operate and why they are considered to be acids, why they're considered to be bases, and what use they are to us in not only chemistry, but of course our day-to-day lives. And so there's two common definitions of an acid and base. The first one is known as the Arrhenius definition. Okay? And the Arrhenius definition in a nutshell states that an acid is any substance that will produce excess H+ ions in solution. Conversely, a base is going to be any substance that produces excess hydroxide ions in solution. Okay? So according to Arrhenius, if we're going to make H+, something, a substance was placed into water and suddenly H+ came out, it's an acid. Again, something was put into water and suddenly OH negative came out, now it's a base. And so what we do is that in the most basic and simplest of forms, the Arrhenius equation is kind of like stating the obvious, right? So we start over here on the left-hand side. What we're going to see is on the left-hand side, we start off with some hydrochloric acid. Let's for a moment pretend I didn't know how to name it, and let's just call it HCl. Now, what we find is that the HCl, when placed in water, will break apart, right? And in breaking apart and making the two separate ions, now suddenly we see the H+ floating separately from the Cl-, right? And so, of course, to me, I could look at this and say, well, this is a no-brainer. Where did the H+ come from? It's almost like I took this HCl and I cleaved it, right? I just broke it up and I separated out the hydrogen from the chloride. So no big mystery, no major surprise there. Likewise, when I come over here and I look at my sulfuric acid, again, my H2SO4, I could see this and I could say, well, I put this in water and now suddenly I produced 2 moles of H+ ions for every 1 mole of sulfate. But again, where did it come from? Pretty straightforward. This hydrogen was separated from the rest of the sulfates. Okay? And this also was very handy when we looked at certain substances known as bases, because when we look at a base, in the example of NaOH or barium hydroxide over here, again, this is where we see it's going to act as a base and produce excess hydroxide, because lo and behold, look, this hydroxide here is now in water going to separate and start floating all by its lonesome over on this side. Okay? And so this is a good example of hydroxide being produced from a substance, whether it's one hydroxide in the case of sodium hydroxide, or over here where we had 2 hydroxides in the case of barium hydroxide. And again, notice that the mole ratio is going to hold. Now, so far so good. I think all of you can look at this and say, this Arrhenius guy, he's onto something. It makes sense. But here's where the Arrhenius definition starts to fall apart. What happens when I have a substance like ammonia? Right? What we find is that when I put NH3 in water, when I literally put the NH3 here into the water, I'm going to end up producing ammonium, this guy here, and then all of a sudden, hydroxide. Well, where did that come from? Where did it pop out of? Because if I look closely here at my ammonia, there's no oxygen anywhere to be found. So how is it that I can produce excess oxygen, right, or hydroxide in a solution if there was nothing there to begin with, right? Like where is that coming from? And so this was the issue with the Arrhenius definition. That while it said, hey, if you make hydroxide, then you must be a base, it doesn't give a reasoning or an explanation as to where that came from or how we got here, right? It's just kind of like, boop, there it popped up. Now, again, it works if we look at something, for example, like acetic acid. So here we have acetate and hydrogen, and even in this case, again, it's this hydrogen that separates out. I can easily isolate. I can find the hydrogen that leaves the rest of the compound. But I don't easily see that when it comes time to look at something like ammonia. This would also show up in certain salts. For example, if I were to take something like, sake of argument, sodium nitrite, right? When I place this into water, what I would find is that I would end up making HNO2 and hydroxide. And again, it's one of those things that you look at this problem and you go, how'd I get over here? How did we make this stuff, right? It's not very apparently obvious where it's coming from. More importantly, you know, I understand where NO2 came from. That makes sense, but then once again, I have these extra hydrogens. And more importantly, well, where's the hydrogen? I don't see any hydrogen over here on the left-hand side. Yet, when we place these substances, all of them into water, everything that I'm showing you on the product side ends up popping out. So, the Arrhenius definition is a great first start. It's like the opening salvo, the opening shot, right? Good start, good idea. At least now we can identify if you make H plus or you make hydroxide, then you're going to be an acid or a base. But to get to the why, to understand more of the mechanism, we now need to take a look at our second definition, known as the Bronsted-Lowry, or technically the Bronsted-Lowry definition, right? And according to Bronsted-Lowry, acids are proton donors and bases are proton acceptors. Now, hang on. I know. You're sitting there and you're saying, wait! I thought that protons were in the nucleus and you couldn't move stuff around in the nucleus. And I would say, you're absolutely correct. Typically, when we talk about things moving around, everything we've always talked about is that you move around electrons. So how is this statement true that an acid is a proton donor and a base is a proton acceptor? And in order to understand that, we need to actually look at our hydrogen atom and see what's going on there. And so in a nutshell, here's how we're going to rewrite our hydrochloric acid reaction. Instead of just having the HCl in water, like in water as the arrow and just saying, look, the HCl broke apart, right? Instead of doing that, what we're going to do is that we're now going to treat the HCl as a proton donor, meaning that the hydrogen nucleus, right, the one single proton of the hydrogen nucleus, is actually going to go and attach itself to this water molecule over here. And when it does so, what we're going to find is that we have our chlorine ion, chloride, left behind, and we make this new substance here known as, what I have listed below, hydronium. And so now the question becomes, okay, what on earth just happened? So in order to help us walk through this, let's take a look at this very complex and again stunning graphic that I've once again drawn for you. I know you continue to be amazed by my artistic prowess. So let's take a look. This is my chlorine, and over here, this is my hydrogen. Now, you might recall that water was a highly polarized molecule. And what that means is that water not only had oxygen kind of pulling all the electrons towards itself, but to make matters worse, water also, or excuse me, the oxygen also has not one, but two lone pairs of electrons. Meaning that it's going to have right here, whoop, a lone pair of electrons, and right here, whoop, a lone pair of electrons. And so this is my water molecule. Now right now I've purposely oriented my water molecule, so if you notice I have all of the lone pairs aiming, right, towards the left-hand side, okay? And why is that significant? Well, because sometimes over here in this hydrochloric acid molecule, what'll actually happen is every so often, our electron cloud of the chlorine, this guy, will actually shift like what we see here. And so what that means then is that for a moment, the electron cloud of my chlorine has really moved away from the nucleus of the chlorine, and in particular, the nucleus of the hydrogen atom. And so now that most of the electrons are on the left-hand side of the chlorine, that means that this electron that was originally right about there on the boundary of the hydrogen's valence shell and the chlorine, well, what we find is that now that electron has actually moved as well. And it's now moved closer to the chlorine nucleus over here. And so when it moves closer to the chlorine nucleus, now you're left with a hydrogen nucleus all by its lonesome. Or, instead of a hydrogen nucleus, I now have a proton by itself without any electrons. So if there's a water molecule in the area, the closest set of electrons, or the closest negative charge, is not the original electron of the hydrogen, but rather it's now going to be the electron pairs on the water molecule. And as a result, what we end up seeing is that the hydrogen nucleus will separate itself from the acid. In doing so, it will now bond to the water molecule. And when it does that, it's now going to create this new structure known as a hydronium ion. And so my hydronium ion is now going to be, in essence, the same water molecule. So here's the original H2, and there's the O, but we've now added this extra hydrogen nucleus, or we've added an extra proton to my mix. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.